Basically, the talk is structured around looking at the current threat landscape, giving an overview of behavioral security, justifying why it makes sense given the threat landscape, give an example of how the traditional rule-based behavioral security system works, and looking at how automated machine learning and data mining techniques are probably a good answer to deal with the threat landscape that we are seeing. And then we look at how we can apply. I'll give a brief introduction to machine learning, both in terms of supervised as well as unsupervised machine learning, and talk about applying machine learning for behavioral security, and talk in terms of some real-world examples. Okay, and then I'll conclude that with some examples of how data mining and machine learning is probably not the only answer. And if and when it has to be applied, it has to be applied with some kind of domain knowledge. And it has to be combined with a whole bunch of other approaches in order to make up for a holistic solution. Okay, so let's look at the threat landscape. In the last 12 to 18 months, again, targeted attacks have gained notoriety, thanks to attacks like Aura or Stuxnet. Social networking platforms provide a very rich source of information through which attacks can be targeted, even to fool most sophisticated users, because the attacks carry a whole lot of context. The attack kits are definitely learning from all the techniques used in targeted attacks, and we expect many of those techniques to land up in attack kits to make up for the attacks to be extremely sophisticated. And we have seen more and more that attacks are using stealth techniques in order to remain dormant and hidden in enterprises for a long period of time, especially as they are becoming more and more targeted towards specific enterprises and have a very specific aim in mind, unlike before where it was about mass infection and getting users' information across the internet. And as the users as we, all these lessons learned on the PC world are increasingly making their way on mobile. So we'll continue to see mobile threats evolve and progress in the same fashion. We've seen a lot of mobile threats increase over the last 2 years, and we expect next year to be in a, the increase to be in a similar fashion. So, what has really happened over the last few years is that the attacks have, migrated away from mass distribution of relatively few threats to a micro-distribution model where fewer number of variants of exactly the same threat are spread across large number of users. So, where we saw Storm make its way into millions of machines across the globe, with the same, when I say millions of machines and Storm, I mean the same SHA-2 was found on millions of machines. What we see now is lots of variants of Window and Hierarchy, for example, propagate again to millions of users, but from a file SHA-2 fingerprint point of view, we saw Window had close to like 18 variants, and Hierarchy had close to 1.6 variants. So if you were to look at from a file fingerprint point of view, you would think there are millions and millions of threats, but they really boil down to the same threat, which is Hierarchy spread across millions of users. So now the challenge for the traditional signature-based security approach is that which relies on a fingerprint, which relies on the fact that you have to have the sample in hand in order to produce the fingerprint, doesn't really fit this model. So what are the odds that a traditional signature-based security solution will be able to discover all these threats? It becomes extremely challenging. Okay. So when I talk about threats and threats being unique at the byte level, what really goes on in a simple animated step is a hacker basically develops a threat. They use tools which are referred to as scripters in order to produce binaries which differ at a byte level in order to evade a signature-based security engine. And most of the attack kits these days come in with built-in functionality to mutate the file to a point where this security engine is no longer picking up the threat. Okay, so they're not going to just produce one and give it back, but they would iterate, and they have a whole bunch of security engines against which they're checking the file, and they'll iterate till they can find a variant which pretty much evades as many security engines as possible, okay? So all this is automated, again, because this is they're trying to evade a signature-based technology. All it takes is install a product, update the product, pull down the latest definitions, mutate the file, test it. If it is detected, then your variant is not good enough. You mutate it again and again and again, and you can do that in an automated fashion. They could be changing a byte, adding a payload, adding a section, or whatever. And the attack kits and cryptos have gotten pretty sophisticated. These are some example screenshots here. Point and click kits. You really don't have to know a lot about them, but you can use them in a very powerful fashion. Here's one example where they're asking the user to supply the hacker to supply the FTP account details or Gmail account details, where the keylogger would start sending information. There are attack kits which have specific switches built in, or options built in to evade specific security vendors. And again, depending on the capabilities of the kits, the price varies. And they have migrated to the cloud model. Of course, the whole industry is migrating towards the cloud. So why download a software? You can submit a file, and you can pretty much take advantage of their pricing models. Like, for $1, you can use 24 hours, submit as many files, and get as many variants as possible that are, again, guaranteed to evade security engines. And then on the basis of the pricing, they'll list a whole bunch of security vendors which they'll test against and guarantee that it evades those security engines. Misleading apps, which has gained a lot of attention over the last 18 months. We have seen examples of these where all that is going on is basically just reskinning of the binary, okay? So these are a whole bunch of misleading apps. You can see it's Windows error correction, Windows Express help, Express settings. They all come with different names, but as you can see, they are just skins on top of the basic same misleading app. So all that is going on is the template for the UI is changing, but the basic functionality of the malware remains the same. So in this case, we've seen, for example, for this particular misleading app, we saw 49 different clones for exactly the same attack that was going on. All pretty much automated in most of the way, all the way from having a web page which supports the product, and you have a 24/7 helpline, 1-800 number, and everything set up in a very automated fashion. Okay, so the point being that the bytes change, but behaviors of these threats really don't change. Password stealers will continue to steal passwords. Spam bots will continue to generate spams. And rogue antivirus will continue to pop up misleading apps for the user to click and download. So in a sense, the bytes are changing, the signatures are being evaded, but the behaviors don't change. So hence, behavior-based detection engines basically take advantage of this basic fact. It is an engine that ignores what the threat looks like, but detects on the basis of what the threat does, okay? So that's the whole point of behavior-based detection engines, and they've been around for more than 2 decades. There is nothing new about it. So before I go into more details, one thing I would like to clarify. Over the last couple of decades, we have progressed from a detection-based industry to a protection-based industry, or a prevention-based industry, but there is a whole lot of confusion around these terms and terminologies. Detection primarily implies, at least in my mind, detecting a threat after the fact that it has done something malicious on the system. And the product has to then take care of remediating the threat, as well as repairing the system to restore the settings. If a registry setting was modified, it has to be restored to the original state. If the file was modified, it has to be restored to the original state. If your, for example, etc host file was modified, all the malicious entries in the etc host files have to be repaired to restore it to the original state. Okay. So it is challenging to offer protection to the end users through a detection-based model, because you are not always guaranteed to be able to repair the state in the original state, right? I mean, a P file modification is extremely hard unless you have a copy or a very smart engine which can reverse the binary level changes. Prevention is before the fact, right? So before the sample runs on the system and does anything malicious, you should be able to detect it, right? And prevention becomes extremely challenging, especially in terms of behavioral-based systems, because how do you detect a threat before it runs, yet you claim it to be a behavioral system, right? So it's pretty challenging, but again, there are ways in which even that model becomes viable. So protection could be both either detection-based or prevention-based, and users can take advantage of either of those models, or security engines can implement both the models in parallel. As I mentioned, challenges are, of course, can all the changes be reversed if you have a detection-based model, and prevention-based approaches. Which action do you block? How much do you monitor? How invasive do you get? And what is the performance overhead of such a model? Okay. Here's something that you need to think about, right? If a malware is doing 6 actions, and you are monitoring all of those 6 actions, but you conclude that it is malicious in the 5th action, and you say, I have prevented the 6th most malicious action that it was about to take, does it convince you of the fact that it is a prevention-based engine? I think only if the first 5 actions that it took were completely reversible by the security engine, then I think it would fit the prevention-based model. And I think that's the more realistic stance, and that is how it should be. I really doubt if there are true behavioral-based detection engines which can block and conclude with good success rates on the first event that they observe, because there is not too much context that they have gleaned over. Anyways, so those are I think all these models can fit in a security engine in parallel. So let's look at the legacy rules-based behavioral security. They are basically rules to identify malicious activity. They could be as simple as things like a file runs from a temp folder, writes to run one's key, creates a file in C:\Windows, and modifies a browser homepage. An analyst could write such a rule. He's pretty confident that there is no legit software that runs from the temp folder, modifies the browser homepage, writes a file to a Windows key, and so on and so forth, and hence it is malicious. Another example would be a file runs from the temp folder, does an open process to one of the Windows service processes, writes into the process memory, and creates a remote thread. Again, if he believes that this is very unlikely a behavior of a clean software, and he observes this behavior across a large population of malware, he could be writing such rules. So legacy systems are simple and intuitive expert systems. They require domain experts to know how to distinguish between good and bad. They analyze the malware, they spot the trends, and they write the rules. And the product may have an ability to even let the administrators or the users interface with the behavioral engine and write rules if they think they can design rules very specifically to tailor towards their environment in an enterprise. The applicability, of course, is many security products, especially in enterprise products, where administrators do want such an ability. And in some cases, this may be the only answer. There might be some threats which can be very easily detected and remediated through very simple rules where you don't need a whole lot of complex specification on what the threat is. The benefits, of course, of this model is that it provides broader coverage than simple signature-based security. It can provide a precise reasoning for why a detection happened and why a particular thing was identified as malicious, because it is backed up by the rule that triggered, right? So you can look at the rule and you can say, okay, this is what all did, that's why this thing was malicious. You can name a threat, and so it could be, again, very contextual. And you can take relevant actions, because now you can say, if these are the actions that it takes, then it is this type of threat, and so in order to remediate, I need to take this action. The action could be terminate a process, delete a file, repair a registry, or simply terminate a file, and that would be good enough. So you can take, or you can just suspend a process. It could be marked a Windows critical process, in which case if you try to shut it down, it's going to reboot the machine. You can just simply suspend the process and take care of all the side effects before you go about terminating the process. So those are the kind of advantages. So you get a lot more contextual when writing these kind of rules. Of course, the disadvantage is scalability, right? You cannot scale because you require human experts to be looking at these threats day in, day out, writing rules, right? And it requires domain expertise. More importantly, does it really imply low error rates? It's really up to the analyst or the quality of the analyst you have. It's mostly based on the gut feeling that they feel that this is not going to trigger on clean software. But that's not true. I mean, people write all kinds of fancy software. Even my examples that I had quoted before, running from a temp folder, writing to a run key, dropping a file in system folder. You can imagine an installer dropping its child processes in the temp folder and taking all these actions, or administrators trying to distribute a patch or trying to do something in an enterprise environment, and we have seen that happen. Okay, so to say that one model provides low error rates compared to the other is merely an illusion, because even domain experts don't really can capture the true behavioral diversity of clean software across the globe. There is a lot of creative talent out there which can do a lot of creative programming. Okay. So back to scalability. So if we conclude that behavioral variants are far less than file variants, and behavioral security model is a good way to address the problem, then what happens when you get a new SHA-2? How do you conclude whether it's a new file variant or really a new malware? The same malware may be packed differently, the same malware may be skinned differently. So is the answer to analyze the thread? I guess no, it should not be the only answer, maybe one of the answers. I think it has to be augmented with automation. You can collect the data and you can mine the data and create models which can offset for the scale of the problem that we are trying to deal with. Okay, so I'll quickly go through some machine learning basics and then show how we can apply machine learning to solve this problem, and how that is not the complete solution as well. Okay, so machine learning is basically an approach to artificial intelligence to get the computer to learn by showing it lots of examples. Okay, so here in this case, given the face, the machine learning model should be able to pick up the fact that the name is Napoleon Dynamite. Okay, in some cases, hand programming is not possible, and machine learning may be the only solution. For example, like face detection. Think about writing a face detection program by hand, right? I mean, what are you going to write? A circle or an ellipse which has two round circles with white and black and a nose and a mouth. I mean, that definition could even fit the face of a human versus a monkey, right? So hand programming may not be the answer in many of the cases. Handwriting detection is another example where machine learning is probably the best answer. So the central question of machine learning is, how can we build computer systems that automatically improve with experience? And what are the fundamental laws that govern our learning processes? And it can be best described as a process which tries to improve its performance at a task T through experience E. And by that experience, I mean examples of the data that you would show, and it will try to figure out how to detect the example by the features of the example that it has been shown, so as to predict what the label or the characteristic of the data that is when you give an unknown example to it. I'll probably clarify that more with examples as I move forward. Okay? So it's basically discovering relationship between the variables of the system, input and the output, and it's trying to detect what the hidden relationships are. So you're giving it an input, and you say this is the output. So when you're trying to train the model, what you're giving it is label data. One basic subfield of machine learning is supervised machine learning, where you're giving label data, and you're saying, here's the data, here's the label. And it tries to discover what is the relationship between the data and the label, such that when you give it an unknown example, it can predict what the label of that unknown example is on the basis of what model it has learned when you fed in the labeled examples. Okay? So the building blocks of machine learning are computer science, statistics, cognitive science, and information theory. And they all ask a very distinctive question, and machine learning basically it builds on all these questions, but poses a very different question. I'm going to move on to more informative slides which are about the problem domain rather than wasting too much time on machine learning. But one thing that is important to note that there are basically four top-level categories of machine learning. One is supervised machine learning, which is, as I mentioned, supervised machine learning is where you give it label data and you give it examples, and it tries to build a model in order to predict what the label of an unknown example is. An unsupervised machine learning problem is where you give it lots of examples, they are not labeled, and the system tries to figure out what relationship exists between those examples. So it tries to build clusters. So classification would be a classic supervised machine learning, whereas clustering would be an example of unsupervised machine learning. Okay? Semi-supervised machine learning is where you have a mix of labeled and unlabeled data. You might have very little labeled data, and you could have lots of unlabeled data, and you're trying to build models and trying to improve the models on the basis of the label data, okay? Because you have very few of them. You try to measure the error of the model that you built on the label data and try to improve it. Reinforcement learning is classic example is robotics, where you kind of give it has a sequence of inputs and actions it can perform, and there is a reward and a penalty model where if it takes a wrong decision, it is punished, and if it takes the right decision, then it is rewarded, and it tries to improve the decision-making process because it tries to maximize its behavior towards an expected reward. So those are the 4 basic categories, and I'll emphasize, and for the rest of the talk, I'll probably be emphasizing mostly on the supervised machine learning, but there is application of unsupervised as well, okay? So the basic steps of machine learning involve, pick a feature representation for your task. You have inputs and outputs, and you're trying to figure out what features relate mostly to the examples and how they help you distinguish between one class or the other, okay? And in our case, what we're really talking about is malware samples, right? So it is a clean sample or it is a malicious sample. If I give you a whole lot of clean samples and malicious samples, what the machine learning is trying to figure out is what are the distinct characteristics that help me distinguish between good and bad. And those characteristics are something that we tend to use our domain expertise and tell that, maybe this is one of the features, maybe this is one of the features, maybe this is one of the features, and it tries to use those features in conjunction to the best extent possible on the basis of the examples to build a model around those features. So it's not trying to build features on its own, it tries to leverage and apply those features in order to come up with the most accurate models. And I have examples to go about showing how we would be doing that. So you do that, you compile the data. By compiling the data, I mean you collect the data, and then you choose the machine learning algorithm. There are gazillion choices of machine learning algorithms. You train the algorithm, you evaluate the results, and you iterate through that process over and over again until you start getting models which perform to an expected efficacy level. There are many choices of tools available, mainly free ones. WEKA is one that I'll be using in my demo. The only problem is it's a Java-based application. It does not scale well to large-scale data. You have, it's got very fancy UI. You can look at the data sets and how the data sets split across various features and so on and so forth. Then you have Orange, which is a native C-based application, has very nice Python interfaces. Again, has drag and drop UI as well. So you can talk using command line using Python, or you can use drag and drop in order to evaluate and load the data and evaluate various models. And the input file for most of these, the color is not very showing up very well, but I'll be showing the example of this. So the input file formats are usually R file, which is a file format, a very simple text file format where it has a header which describes what the features are, and then comma-separated values of each and every example that you might want to represent using those features. And TSV file is just tab-separated or CSV files. Any of those would be the type of typical input files, okay? So now let's see how we can apply machine learning to behavioral security. So the goal here is to train a model and provide automated and meaningful information about unknown samples. That's really what the goal is, right? So you're getting inundated with lots and lots of samples coming in, and you want to now train a model in order to offset the demand for domain experts to be looking at each and every sample, right? So you want to offload that work a little bit to automated machine learning-based systems. The 2 goals that you may want to fulfill, one could be just identify a class or a label. You might want to say this is good or this is bad, or you might want to identify an association. So you might have a collection of threads of various families, and you might want to know whether this new incoming sample closely resembles which of the various thread families that you might have in your collection. Okay? So one would be a classification problem, the other would be a clustering problem. So basically, application of information extracted implies over here that we want to classify the sample or provide information to the analyst for the purpose of labeling or writing definitions. So either they can just use that information and improve the quality of the engine, or you could directly use a model in order to build a real-time prediction engine. Both of the applications are something that is going on in the industry today. So in terms of machine learning, the steps that I talked about generally in terms of machine learning now would involve, you would collect the samples, And when I say samples, I mean labeled samples. So you know that these are malicious samples and these are valid samples. You would set up a VM with a monitoring framework. So a monitoring framework becomes pretty critical to how you would go about using this going forward, because you don't want to build a monitoring framework where you want to take the model extracted out of that framework and then apply it for real-time protection, because you want the enforcement and the collection points to be very close to each other, almost the same. And that will be clear through examples again. You would then push and run the samples in some kind of automation system that you would have built on a farm of virtual machines. You would collect the sample behavior data. You, of course, would want to recycle the VM because as you run malware, they're going to make changes to the system that you don't want to show up in the next run of the next sample. You extract the information in a format suitable for data mining. You train the models, and you test and deploy the models. And again, when you deploy the models, you're either deploying it merely for information extraction or you're deploying it for real-time protection. Okay, so here's an example of what the monitoring framework could look like. It could simply be built on something like detours using user mode API hooking. And it could collect information like the API name called, right? So you could hook pretty much every export of kernel 32 and log the API that was called. You could also collect the parameter information. You could collect information like which API called this API, state of the process, etc. You could extract the features and extract the features out of the log files into what is the R file, right? R file, TSV file, CSV file, whatever suits your machine learning technology that you're going to use. And the features that you could extract are things like has UI or a window, right? Does the sample have a UI or a window? I mean, most of the malicious samples, for example, bots, may not have any user interface element. Now, that's something that I'm expecting domain experts to come up with. So a domain expert might say, yeah, I mean, for 80% of the cases, I don't see UI on top of malware, so that is an interesting feature. So that's what I meant by creating features using domain expertise. Okay. Does it do network communication? Does it talk over IRC? Does it talk over HTTP? Is it registered in an auto start location, right? So run key, run once key, service enabled, and so on and so forth. Does it create a Windows task? Does it modify a P file on the system? Does it create a P file? Does it inject into trusted processes? And you can have a definition of trusted processes, like I mentioned, Windows Service is an example of a trusted process, okay? So these are the kind of examples of features that you might have, which you want the machine learning system to take advantage of and figure out what combination of true and false on these various questions you want to ask about good versus bad sample should be combined in order to come up with a model that can very accurately predict whether this unknown sample is clean or malicious. I'm not sure whether everybody can see this clearly or not, but basically the features that I have in this R file that I've created are things like create window, show window, find window, shell execute, delete file, move file, create file, HTTP send request, device IO control. So these are all the hook points for various APIs. State information that I'm collecting are has a window, does it have a listening port, does it create tasks, does it modify a P file, creates a P file, does it inject, is it registered as auto start, and the last attribute is how long has it been created since, okay? So what I'm trying to do over here is trying to build a model on the basis of these various characteristics of a sample. And created since seconds is an interesting feature. You can pretty much say that malware is usually very interested in doing a malicious activity as soon as it lands on the system, okay? Whereas a clean software doesn't necessarily have to take any action. It might be sitting there, user launches it. It may not take any action until the user interacts with the application and so on and so forth. So that itself might be a very interesting feature that you might want to use in conjunction with all the other features in order to distinguish between good and bad software. So a sample that does a whole lot of activity in a very short span of time might look more malicious than a clean software that does very little over a long period of time because it requires user interaction constantly. Okay, so let's see if I can do the demo. Okay, so here's WEKA, and WEKA is one of the tools that I've mentioned. And I'm going to launch the Explorer. And I have built the R file from basically from around lots of samples that I've collected, like around 90 of those. So here's the R file, okay? So when you load an R file, as I showed the R file, how it looked like, pretty trivial to create. Here are all the various features. And if you look at the class, which is, the class is basically on the last line of each and every data point that I'd collected for each and every sample, I have M or a V saying that this data is about either a malicious sample or a valid sample. I have 47 good examples and 42 bad examples, okay? Once I've loaded the data, I basically can use a whole bunch of built-in machine learning technologies or modeling technologies that are available. I'll pick one very commonly used, which is J48 or decision trees, because the reason decision trees are good is because you can see how it arrived at a particular conclusion by looking at the various, walking down the tree and saying, okay, how did it make a decision whether a particular sample is malicious or not, and you can reason about the model. The other models provide you with a mathematical polynomial function, and it is very difficult to reason about how did it arrive at that model and say that this file is malicious or not. So I'm going to use J48, leave all the default options, and all I have to do is hit start, and it creates a model, okay? I agree that the efficacy of the model is pretty bad, 63% correctness and 37% error rate. Nonetheless, the data set was very small. This is not a data set on which you would be training a model that you want to deploy in production. But if you look at the model that was created, if it look at some rational decisions it arrived at. If it created a file and it was created in less than 6,000 seconds, and if it did a send request, then it is bad. And there are 19 examples which did that, bad examples and 3 good examples. But if it did not do an HTTP request, and it was registered at an auto start, and it did try to find a window on the desktop, then it is malicious. I have 8 examples of those which does that and 0 valid examples. So those are the kind of things you can observe from the model that it builds. Again, the more data set you give, the better quality of the data set you give, better models you get. Okay. I was going to go through an orange demo as well, but I don't think so I have enough time for that. So basically, once you build the classifiers, you want to apply a classifiers. I mentioned, there are hook points on which you're going to collect the information, and there are hook points on which you're going to enforce the decisions that you derive from the models. And they may or may not be the same. One could be simply for collecting the information. The others could be simply to leverage that information, evaluate the model, and take an action, because not all hook points are suitable for taking a block action. Okay? The result of trying to take a block action might depend on modifying an out parameter of the API call versus returning an error code and so on and so forth. So you might want to decide which APIs do you want to take a block action on and which APIs you want to collect information on. Okay. Again, which APIs to hook? Do you want to hook a higher level API which allows a lot of granularity, or do you want to hook a lower level API? Again, lower level APIs could be very chatty, right? Because lots of high level APIs filter down to some lower level APIs. What kind of block action do you want to take? Failing an API, or terminating a thread or process, or modifying an out parameter? Those are all the various choices of block action that you might want to take. So, that is how you could use, but reality is it doesn't really work out that easily, and you cannot really go about applying it without understanding what's going on. One interesting thing that we observed was lots of samples fail to run in automation. And more importantly, good samples fail to run in automation than bad, because bad samples are fairly standalone. They don't have much dependencies. They'll run very easily. Good samples, on the other hand, have lots of dependencies. They might be dependent on configuration. So if you get a good sample, but you don't have all the other dependencies or the configuration that it expects in registry, for example, it may not run. It may fail to run, right? Or it may require user interaction. Again, in an automation, if you're launching an EXE and if it is waiting on a OK cancel dialog box, and you leave it running for 10 seconds and say, OK, I'm done with automating this sample, it hasn't really done anything. It hasn't launched. It was waiting for user interaction to happen. Okay? So GUI automation and dependency config could be some of the challenges. Many samples, malicious samples, on the other hand, deliberately fail to run in automation. They have VM-aware capabilities, right? simple instructions in order to detect virtual environment. They might check their own file name. They might check the parent process. For example, is my parent process IE or Explorer? And if it is not, they'll fail to run. They might check application settings. For instance, in this case, they were checking for IE extensions whether they are enabled or not. And if they are not enabled, the sample does not run. So they're getting pretty clever because they want to evade automation to a certain extent. Okay. Samples may be stale. If you're running a very old sample, the CNC server might be down and the sample may not run. Just check the network connection. Network connection does not succeed, it exits. Doesn't mean that it is clean because you have really not seen its full behavior had it connected to the CNC. And then they are sensitive to system state. They might be missing dependencies. Like clean software might require .NET or Java to be installed on the system. Malicious samples might be targeting a specific third-party application like Adobe Reader. And if it is missing from your VM setup, then the sample will fail to run. Okay. And then there are challenges in machine learning, like imbalanced data sets. You have lots of good examples, very few bad examples, or vice versa. You could have features missing, and you might try to parse a PE header file, and it might be such corrupted that you might not be able to collect all the features. There might be anomalous features, right? Now, in classic machine learning, what happens is anomalous features are usually considered outliers, and model builders usually throw away the outliers. But in our case, you have to stop and think whether the anomalous value is a feature that you want to take advantage of and has been deliberately put in, or is it just a matter of wrong data collection? A large section size, for example, is a very common technique used by malware to evade reverse engineering because IDA takes a long time to load that file. And a classic machine learning guy without any domain expertise is going to say, oh, that's outlier data. I don't want to train on it. Whereas one with domain expertise is going to say, no, that is interesting because that never happens in clean. And I know that it happens in malicious files because it is a classic anti-reverse engineering technique. So we should use that as a feature rather than try to throw away the data. So you have to kind of combine both domain expertise as when trying to build machine learning. Okay? And here are some examples. The other challenge is going to be non-process threats, right? So threats which are not a process by themselves. Code versus data. A malicious PDF file is going to make Adobe Reader behave maliciously. So what are you really going to treat as malicious, and what are you really going to remediate, and what are you going to learn on? So machine learning, as I explained, as is, does not really apply to NPTs. But there are ways in which you can get around that problem. Like there are lots of examples of non-code files which are known to be malicious or encode and exploit in them: help, link files, MSI, MSPs, screensavers, .reg files, and there's a long list of such files. DLL's classic example, though they are PE files, but they're running in the context of a trusted process like run DL32 or redserve. So redserve is not malicious, but the DLL that it runs is malicious. But if you observe the behavior of run DL32 and say, it did all this malicious activity and hence it's malicious, you ought to relate that to the DLL that it loaded on the command line, not to the process itself, and take a corresponding remediate action. Okay? So how do you automate these? That's probably one of the biggest challenges. And there's a decent population of non-process-based threats that come across all the time. How and where do you enforce the protection? And what is it that should be remediated in these cases? All these have to be decisions that you have to work into the solution as you try to automate. Okay? So in terms of conclusion, what I would say is, behavioral malware is not evolving as fast as the files are, right? So we see millions and millions of files in a very short span of time, but behaviorally the variants or the threat families are not evolving that quick, and automation is probably one of the solutions, not the only solution, one of the many solutions in which you can deal with the scale of the problem. But you have to be aware of the pitfalls of automation. You have to realize what works and what does not work, and when it doesn't work, you have to identify the fact that it might be deliberate in the nature of the problem that the sample is failing in automation, okay? So just because the sample does not run doesn't mean that you give up. Again, examples that I cited, for example, where it is checking the parent process being IE, right? How many clean samples, for example, are going to check that, right? So if I can capture that behavior as a feature, even though it does not run, that the presence of that feature itself might be very conclusive to the fact that it is malicious. I don't know of any clean software that tries to check whether its parent process is IE and then fails to run if it is not launched from IE. Games maybe I could think of. So the challenge really is what if the malware is a valid application with a configuration file, and that is all that is, right? I mean, if you get a malware which is a valid application and it comes down with a configuration file which causes it to behave maliciously, then what are you really trying to train on? What are you trying to remediate? I have an example of, I don't know how many are familiar with GTBot. GTBot was an MIRC-based bot, and it dropped an MIRC application with a config file. And the config file was able to direct the MIRC application to connect to a chat room and take various actions. So it's not manipulated. Its checksum exactly matches up the original MIRC, and it's a config file which is really driving the malicious activity on behalf of the MIRC application. Now, if you were to automate that, you might conclude the fact that that MIRC application is malicious. But if a signature analyst gets hold of the fact that you've concluded this file is malicious, they might issue a signature on the basis. They might issue an AV signature on the basis of the checksum of the file. And that is the mistake you want to avoid, because it's not the MIRC app which is malicious, because then you would release such a signature and it would wipe off MIRC across all the users' machines. It's a combination of where the MIRC application was dropped, where was it running as, and where was it loading the configuration information from, and so on and so forth, that made it malicious. GTBot was running from Windows folder, by the way. I'll probably post a video of that in the speakers area. So those are the various challenges, and to conclude the fact that, though machine learning is one of the ways in which you can deal with the scale of the problem, you have to use machine learning with a combination of domain expertise in order to make it a very compelling solution. But nonetheless, it's not the only solution, and it has to be augmented with many other approaches. Any questions? I know I went pretty fast.